Thank you for the invitation to come here. It's first time in Wales. This is very exciting. What a train ride. So I'm Ken from MIT, although I will let some of you in on some news that I'm actually moving to UC Berkeley next summer. So that's where I'm from, actually. So all my family's out there. So hopefully I'll get some free grandparent childcare. So this is a subject matter that I can honestly say I've never given a talk on before. So this is your turn to really poke. But this is when I saw that the topic was hackings, I thought, okay, maybe this is the right crowd for this material. So I'm going to break this into two parts, and I'm going to try to hit 45 minutes as instructed. So the first part, so the topic of my presentation is how to get some novel ways to get the forces in DEM, right? So this is going to be about hard particle DEM and how you obtain the forces in these packets. So the first part of my talk, I'm jokingly referring to as rigid elasticity. Okay, so this sounds like an oxymoron. Yes, already, wow. Okay.
I don't know what the acronym DEM stands for.
Oh, you're going to see in the next slide.
Okay.
There you go. See, this is, but do ask questions in the middle like this. This is good. Okay. So, see, told you. Okay. So when you have a packing of particles and you need to figure out the force between them, you have a couple of ways that are sort of typically done for this, right? And I would say almost certainly the most common is this thing that we call DEM, or the discrete element method. And I'm just going to call it DEM for this presentation. And it refers to the method where you treat the grains as soft objects, okay? So here you've got two grains, and they're separated by some gap, which is minus the overlap, delta N. So in DEM, you typically press them until you imagine that they actually overlap. And the overlap distance becomes the way that you figure out the force. So you think of it like a spring, right? You actually press them into contact. Okay, so when you use the discrete element method to figure out the forces between grains, you basically get the normal force from elasticity, and you convert that from the overlap. So you can use either Hertz's law or some other contact relationship to convert the overlap distance into a force, okay? And the tangential force is also given from a displacement. It's from an elastic plastic tangential motion during contact. So you say contact forms, they overlap, you get a normal force. And then if you start to shear one against the other, from that point, you measure the tangential displacement. You can put a spring there, okay? And that will give you then a tangential force up to some limit, some Coulomb limit. And so it's, generally speaking, you could say the discrete element method says that the normal force is some function of the overlap when the overlap is positive. Otherwise, it's just nothing, you're not touching. Tangential force is some function of the elastic part of the tangential displacement. Otherwise, if you're not overlapped, it's nothing. And then there's some slip that you have to add to this if there's a frictional sliding criterion, and the total of this is the total delta T. Okay, so that's my warm up to the Kundal-Strack discrete element method. So if you have a packing of particles, you'd actually let them overlap, and you would follow those overlaps, and that tells you the forces. Now that can be contrasted with the other method people use, perfectly rigid grain modeling, also known as contact dynamics. Okay, so in contact dynamics, I have two particles, for example, and I say you are not allowed to penetrate. I treat you as perfectly rigid. Okay, so you touch. There's some force, and it's going to stop you from penetrating. All right. So no penetration is permitted. Okay. I require certain conventions on sign. Right. So normal forces must be non-negative. You cannot pull on sand. Right. That's very important to a dry granular material. You can only compress. Okay. The tangential forces are bounded by friction. So once I have a normal force, there's a limit to how much I can shear. Okay. And you have this important thing called the complementarity condition. Okay, so here's complementarity. It's a nice long word that says, if I'm in contact, that means the gap is zero. And when the gap is zero, only then can I have a positive force. Okay, and conversely, if the gap is positive, that means I have to have a zero force. So they can't both be positive at the same time. That's the complementarity condition. All right. So what's interesting about rigid particle mechanics is you have all of these rules about what the sign of each thing needs to be and when, but you actually have no explicit formula for the contact force. It can be anything that satisfies those rules. Okay, so this is rigid particle contact dynamics written mathematically. This is the complementarity condition. These are the sign constraints. This is the rule on friction, so on. Okay, so let's talk about the sort of dilemmas that emerge when you compare these two ways of doing particle force modeling. So here's the dilemma as I see it. Okay, so in a lot of the world of hacking problems, see, little brand marketing, the grains are usually pretty stiff, right? Really stiff. If you think about like sand, for example, those elastic deformations are so tiny, right? Yeah, really tiny. So typically we want to model those kinds of grains. Now to use DEM, that's the soft particle approach, this requires really small time steps because you're resolving microscopic overlaps to figure out that force, right? Okay, so when it's very stiff, it can be very slow, all right? Now contact dynamics, because it doesn't have that stiff elasticity, can get by with much larger time steps, okay? So it can be faster, but the problem is that you lose some physics because you got rid of the elasticity, okay? So this is a dilemma, okay? Do I want to be fast with less physics or slow with more physics? So what are some things that you lose because you've lost the elasticity? Okay. So here are a couple examples of the physics you lose. Number one, contact dynamics, you can't do elastic waves. So if I give you a string of beads and you tap one side, instantly everything feels it, okay? Because there's no sense of there being some sort of stiffness that causes a wave to go through. And but in hacking, maybe you're not interested in propagating waves, maybe not. You just want to know the packing dynamics. You want to know how the particles flow, for example. All right, if that's the case, then you're more concerned with the second issue, which is that contact dynamics loses contact force uniqueness when you have a dense, or shall I say, non-isostatic packing. Let me show you what I mean. Here's a great example. Let's just say frictionless for the time being. So suppose I've got 4 grains, and I'm going to fix these 3 grains. That was soft contact. It's actually pretty hard. It's exactly right. Okay. And so this grain is loose, and I'm going to apply a force to it. All right. And the question is I want to figure out what are these 3 contact forces. Okay. So let's suppose I'm in the world of contact dynamics. How would I do that? All right. So how many equations and how many unknowns do I have? So I know that I'm in contact with everything, right? So I don't have to worry about the complementarity condition. The gaps are 0 and I have positive force. The question is, what is the force? Okay. Well, this is my only free particle, and it's got 2 directions of force balance. So I've got 2 equations. Okay. But I've got 1, 2, 3 unknowns. So what's the forces? The correct answer, I don't know. Okay. So when you run a contact dynamics solver, it literally just finds one of them and says, how about that one? And moves on to the next step. So the problem is there's no uniqueness of the force there. Now, why is it then that if I switch to DEM, I get unique forces, right? Now, remember with DEM, you should imagine there's overlap. So literally, when you press on this thing, it actually causes the particle, you imagine, to overlap its neighbors, okay? And by doing that, there's now a geometric relationship that says this overlap will be a certain factor of this overlap, right? And when it does that, it means that it's going to specify some ratio between all the forces for you, right? So if you want to look at it mathematically, yes, there's still 2 force balance equations here, but I have 3 force overlap relations. That's like my spring relations. So for a total of 5 equations, okay? And yes, I have 3 contact forces, but now I have 2 displacement components as well, which are also unknowns for a total of 5 unknowns. And this has a unique solution, right? Green check mark. So here's the question. I want to do contact dynamics. I wanted to find this solution, but I don't want to have to track those tiny overlaps. I want to treat them as rigid particles that somehow have some knowledge of elasticity to find these answers. Can we figure out a filter for CZ solution that leaves only the physical, that is the elastically compatible forces, while still maintaining all of the contact dynamics rules of no penetration. Okay, because that would be sort of my best of both worlds solution. It would recapture some of the physics I lost, but still stay at that nice fast contact dynamics time step. All right, so let's build up how to do this from simple things. Let's start simple and then I'll show you the general algorithm. So at first, let's consider 2D particles, but they're dense. Okay, so this is not isostatic. Isostatic would mean that there's so few contacts, there are the same number of equations as unknowns even perceiving. So this is very dense. So here only elasticity would give you a unique solution. Okay, so you have a 2D dense, non-isostatic pile of elastic. Let's start frictionless. Keep it easy. And let's say it's in equilibrium, so everything's touching. I don't have to worry about the complementarity condition. I know everything. I know all the gaps are zero. Okay. The question is what are those forces? So what are the equations of DEM? What would DEM solve to get you to this? Let's just codify all the equations together. So the first one is force balance. Okay. Particle-wise force balance. Every particle must satisfy some of the forces is zero, obviously, right? So if I wanted to assemble all the force balances for every particle into one system, you could write it this way, where D is the so-called assembly matrix, okay? So that's, if you think about this, this is matrix times a vector of normal contact forces, that's the unknown that I'm solving for. External force in this case is gravity, or from the sort of bottom holding it up, okay? And this assembly matrix is NCY, that's the number of contacts, and 2NP tall, that's twice the number of grains because I'm in 2D. Okay? And if it's really dense, the issue here is that NC is really big. I have lots of contacts and not enough particles. Okay? And that's why this system is not on its own invertible. If it were, that would be isostatic. But I still have to satisfy force balance. That's the first thing that I must satisfy. Now, in elasticity, I then have the following. So DEM would tell me that I have a second set of equations. This is the displacement to the force relationship, okay? So there is some vector of tiny extra displacements I should imagine adding to each of the positions of every grain, okay? Such that when the transpose of the assembly matrix hits it, that's what's so interesting in mechanics, you learn this rule. The matrix that sums forces on particles, its transpose takes displacements to overlaps. Did you know that rule? It's a cool math thing. This is math, right? You can prove this, you should prove this. So it's actually just the transpose of the same matrix. All right. So the transpose of the assembly matrix times that extra set of displacement vectors corresponding to each grain gives me the overlaps between the grains. Now, if I believe in elasticity, those overlaps are a function of the forces, right? So just like I could say force is given from overlap, you can invert that, okay? And so each overlap is some function of the force. And if it's elasticity, that function is the derivative of some complementary energy function. Just some function, g of f of n, and its derivative gives me delta. Okay? So this is the mathematical statement. So let me return to my question and state it now according to these mathematical statements. I want to find that vector f. It needs to satisfy both sets of equations above. But I want to find it without ever having to calculate u. I want to get rid of that step and somehow have it find the solution that I would have gotten otherwise, but without having to calculate u along the way. Okay? And that is to say, we want force-only compatibility conditions that will filter out the forces that could never have come from 2. Right? So do you see that 2 is actually a constraint? Why is it a constraint? It's because this matrix is not square. So it's telling me that these forces must be expressed in terms of displacements, but there's actually fewer displacements than forces. So this is actually a constraint, right? You see that that's a constraint. I want to somehow annihilate or eliminate that part and just turn it into a set of constraints on forces. So how do I do that? So any questions so far? Does this? Yeah.
What happens in 3 dimensions?
We'll get there. Yeah, so we're starting, it's a great point. We're starting, the answer in 3D is not too much different. You still have an assembly matrix whose transpose switches to the displacement force relation, displacement overlap relation, yeah. But we'll start with 2D because I can draw it easier, frictionless, and where I know everything's in contact before we start getting rid of all of those. So, math, Hey, math, right? Remember Lagrange multipliers? Oh boy, oh boy, oh boy. Okay, here we go. Let's look at the thing in the box together. So let's say find the solution to df plus f external equals 0 that minimizes something. So the solution here, the first part of what I said, that's the force balance equation from my previous slide. That just says find, so let's look at all the forces that satisfy force balance. That was my equation 1 on the previous slide. Of those, I want you to look at this function E that sums the complementary energy. So for every candidate force solution, I can sum the complementary energy from those forces and get some scalar E. What is that? What happens if that function is minimized or maximized over the set of all possible forces that would satisfy force balance? Okay, let's just do a little walk down memory lane of how I would, what condition would be met by the solution for F that minimizes E. Okay, so this is constrained optimization, right? I have some function that is constrained to live on some space. All right. So let's look at some vector of Lagrange multipliers lambda. Now, if you remember how to do optimization subject to a constraint, remember what you do, you take the gradient of the cost function, you set it equal to lambda times the gradient of the constraint. Okay. So this is the gradient of the constraint because my unknowns are F. And because this function was just the sum of the G's, then it just turns into this list of partial derivatives, right? But remember, each of these partial derivatives, this is the derivative of complementary energy with respect to the force. At each location, that's the overlap, right? Okay, so this is the gradient of the cost function is supposed to be equal to lambda times the gradient of the constraint. But what's the gradient of this with respect to F? It's D transpose. And I get this. But what's this? That's my equation 2. Okay, so I look at this and I say, okay, hang on a second. The solution to this optimization problem, which has no mention of displacement whatsoever, none, there's no displacements in that. If you can optimize it, if you can find that minimum subject to the constraint that it satisfies force balance, you will have found the forces for which there would exist some displacements that relate the forces back to the compatibility condition, okay? So this is our desired force-only constraint. That minimization problem is my force-only constraint, okay? So now I get to tell you why I call this rigid elasticity, right? Remember, I'm interested in the stiff particle limit, okay? Notice that if I go back to what this condition solves, right? Look at that optimization. Suppose I took all of the functions g of fi. Let's just say I took g of fi. I multiplied all of them by 2. Would it change the optimal f? No, it would not. Do you see that? All it does is it scales the cost function, but not where the minimum is, right? I can multiply the whole thing by 1,000,000. It won't change the answer, right? So really, I can start with really stiff particles, like the limits of stiffness going to infinity, and just divide everything out by 1,000,000,000, and I'll get the same answer, right? So actually, I can define the scaled complementary energy function just by multiplying the actual one by some small scalar, and just use that instead, so that everything's order 1 in my solver. There's no need for the billion-sized stiffness, and I can just sort of add a little. There, I made that real slow. There we go. Add a little tilde. Okay. So there you have it. So what I should do, according to this rule, is first find the set of solutions that would satisfy force balance. Then among them, find the one that minimizes this. And that's the one that had to correspond to elasticity. Okay. So now, how do I modify the contact dynamics algorithm based on what we just learned? Okay. So contact dynamics is going to say the following. What do I know? At a given time step, the particles have certain positions and certain velocities. All right. And my goal is to compute the contact forces. And once I have contact forces, the sum of the forces will then be used to move the particles. So that everything is what's those contact forces. Okay. So here's what I propose to do. And this goes back to your question of how we, now everything I'm going to say is now going to be applicable all the way up to 3D. Okay. So step 1, do what I call a classic contact dynamics step, right? Where the first thing that you would do is you would look at your system of particles and try to figure out candidates for where all the contacts are, based on where they are right now and how they're moving right now. I say, okay, I think that might touch, that might touch. Just find a set of particles that could touch in the time step. Isolate that set of particles. Once you've got that set, you can then build the assembly matrix from it. Okay, so now I know where all the particles are that might touch. Let me build the assembly matrix from that. Because now I know where all the normals would be between contacts, right? Step 2, find me a feasible force solution among those possible systems by solving the complementarity equation. Okay, so find me a set of forces that would satisfy force balance among all those particles, but would also satisfy complementarity. So that is, if there is a force, they must be touching. They must touch in that time step, right? If there's no force, then they're allowed to separate. Okay, because I found candidate contact. They might actually be separated. They might not support load during that time step. They were just candidates, right? So I have to solve the complementarity problem, okay, to find one feasible solution, right? And so if you say, how would I do that? The most common way to solve contact dynamics complementarity is actually another minimization problem. You do it through optimization, okay? And I'm not going to get into too many details here, but one way to do it is to solve this equation, okay? So you minimize this quadratic function subject to these constraints. First constraint, of course, is that the forces can't be negative, right? They can only be compressive, right? So negative in this case would mean tensile, so there's no tension, only compression, okay? And so what this will do is it will find me one feasible solution. Now the issue is, remember, that this M matrix here, which is related to the D matrix, is not invertible, okay? So there are many possible solutions to this. Remember, we're in that world where there's not just one answer. So I'm going to find a candidate solution, F star, but I know there's actually a space of answers that it could have found. And it depends on what solver I use, which one it likes, okay? That's the issue with contact dynamics. There's not a unique solution, right? So how do we make it unique? Because I take that solution, okay? And then we apply the compatible correction step. So now what I do is I say, take the solution F star, and here's what I want you to do. Solve another optimization problem. So if I had to use an optimizer any way to do this, just run it once more. So to run my algorithm, it takes exactly 2 times as long as it takes to just do regular classical contact dynamics, okay? So what you'll do is, the actual answer, which is the one that truly updates you at the next time step, is the one that minimizes the complementary energy of the system, subject to make sure that you don't violate forces being negative, and that you get the same answer that you would have gotten up here. So this condition here guarantees I'm only looking at forces that would have given me the same objective function. So every solution to something that balances forces has to give me the same objective function. So this says live in the space of everything that would balance force, okay? And of those, find me the one that minimizes the energy, okay? There it is. This is the compatible contact dynamics algorithm. How does it work? Let's have a look, okay? So I'm still frictionless for the time being, okay? So it's contact dynamics, so things can move around now, right? I'm not just living in equilibrium, right? So let's suppose I take a problem where it's like I want to make a pyramid of particles. So I drop them in until I find that so this is the velocity as I drop in this system of particles. And this is highly over-coordinated. So this is really non-isostatic. Okay, let's have a look at how we do. So this contact dynamics on its own would have a lot of possible solutions. So on this little, this is also known as the cannonball packing, the famous indeterminacy of the cannonball packing problem. Okay, so we ran a bunch of really stiff DEM simulations where there were overlaps. They're just very tiny, okay? And we compared them to compatible CD, right? And we're gonna play with this. So remember, I have the right to tune the contact relationship that I think is there, even if I'm not tracking the displacements, right? So I could say, hey, all the contacts are identical but Hertzian, so it's a nonlinear contact relation. Or for fun, what I could say is every other particle has a different stiffness, but it's Hookean. Okay, so there are stiff particles like steel and slightly less stiff particles like aluminum. Okay, and steel on steel has one contact stiffness, aluminum on aluminum has a different one, steel on aluminum has a different one. Okay, but that's fine. I can tell compatible CV the apparent stiffnesses or the stiffness relationships. It can give me the forces without ever worrying about the displacements. Okay, so This is what it looks like if you say the particles are all Hertzian. So this is what I'm highlighting here, the colors, the contact force magnitude. Okay, so you can see this is Hertzian DEM versus Hertzian compatible CD. And this is multi-species Hookean. That's like you've got every other particle is a different stiffness. And this is, I told the solver in the assembly that that's what I'm doing. And this is from CD. And let's say if you actually want to look at it more carefully, let's look at the floor pressure, okay? Because that really gives it away. So on the top is if all the particles were Hookean, if all the particles were Hertzian, and this is the multi-particle one that I just showed you, right? This is the floor pressure. So that's DEM on the top where there actually were overlaps. This is compatible CD. So you can see that it's exactly matching DEM, which is exactly what it was designed to do. Now, if I just done classical CD, the answer would have been algorithm dependent. Okay, so this is the projected gradient solution to classical CD. This is the Gauss-Seidel solution. Now notice, none of them change as I move this way because they have no idea what contact stiffness means, right? It's just finding me a force balance solution, right? And you can see these are very variable. It just depends on however it minimized to something that didn't have a unique minimum, right? And so what's nice about this is the fact that, let's look at the difference in time steps. So you can see compatible CD matches DEM, but it did so with a time step that was about 2,000 times bigger, right? Because, and in the limit of perfectly stiff particles, it's going to get even worse, right? Now, granted, you might say, well, but CD, you have to solve an optimization problem, right? And, DEM is just dumb. Each step is easy, right? Sure, okay, but still, that optimization problem is not that hard, okay? Like, it's not, so it depends on how many grains you have. If you have a quadrillion grains, there may be some competition between what's better. But if the grain, depending on how big your packing is, in many cases, you can really get away with something if you use CD. Let's see, I'm looking at the clock. Let's say you want to add friction, you can do the same thing. There are some open questions here. This is the thing we're working on now. But basically, we're going to do the same two-step type of thing where the first step is you do classical CD to get a reference to compare against. Then you say, that's what the minimum looks like. Search through the space of everything that has that minimum and now minimize the cost, noting that these forces could have now normal and tangential components, and the cost could depend on both. The energy can be given by both of them, right? So there's two kinds of springs now, and each has a complementary energy. So I have to minimize that whole thing. So, for example, this is the Goldenberg problem. Goldenberg and Goldhirsch did this problem where you've got a packing of I guess they use spheres, and you have gravity, and then you press on this particle in the middle, and then you ask, what's the contact pressure on the floor? And you can change the friction coefficient and see what answer you get, okay? And so here, DEM is the black, as you can, obviously. If you just do regular CD, this is projected Jacobian, you'll get the red, and compatible CD gives you the blue, right? And what's interesting is you can see that compatible CD and DEM pretty much always agree. You get sort of two peaks in this case when the friction coefficient is low, and that sort of converges to one sort of rounded peak when the friction coefficient is high. And regular CD kind of gives you something, but not quite exact. Okay. So some conclusions here. There it is. Last the conclusions. Wanted to try and enter the conclusions. So we have this algorithm now, which is basically a correction to contact dynamics. And it gives you, we make the CD solutions elastically compatible. All right. It allows much larger time steps. It can replicate the solutions of DEM, but without having to deal with DEM. Okay. And it works for frictional and frictionless grades. Yeah.
You did mention all the problems that you're using here are pretty much static. Your evaluation is static, and you did mention wave propagation. Maybe I missed.
So yeah, I can't do wave propagation. It's still CD. So yeah, it's still CD. But I can do motion. I can do flow. Okay, but there's still no sound speed. Okay. You need a real stiffness to get a sound speed.
Go ahead and see that. Yeah.
That's right. That's right. So any other questions on this part? let's see, with every talk that you've never given before, you never know how long it takes you. The clock on the wall says 40.
It's
How much?
another 10 minutes past, actually, so we.
So-
ate some.
Oh, okay. Oh, okay, so I have some time.
Yeah.
Well, I'm gonna continue until somebody tap dances with a hook and just sort of drags me off.
Since you're pausing, I have a question.
Yeah.
Which is more a comment, but I'll ask you a question. The extra kernel, you could say, I mean, the ambiguity in
Yeah.
I think it's reflected in the fact that you can remove particle also.
Yeah.
I just wanted you to comment on that.
Yeah.
It's a different way of thinking about it. You're basically adding a quadratic.
That's right.
to a degenerate problem. So
Yeah, it's a degenerate problem. So the first problem is positive semi-definite, right? So the optimum is not unique. There's like a trough, and I'm finding anything along that trough. And the second part is saying, isolate all the solutions in that trough, find the one that minimizes this other thing. That's the answer, right? Yeah, so this is really an issue in highly consolidated granular packings where you've got too many contacts. If you were careful, you could remove particles and get yourself to the so-called isostatic limit, where you've gotten lucky in that you've removed just enough particles that the first system I wrote was square. Then you wouldn't need this correction. But even if you added the correction, of course, you would still get the right answer, because now there's one point that you're searching through, and yes, it's the minimum, right? Yeah.
Maybe just to follow up on that.
Sure.
Does the forces you find, does that tell you something about going back to figure out what that isostatic network of forces would be, right? Are those two problems related?
Sorry, which two problems? If
The one where you start plucking things out so you get to the
Oh.
square.
Yeah, I mean, you could keep doing it, right? So let's suppose you remove particles and you rerun the algorithm, right? If you keep removing, let's suppose there's some set of particles you're going to remove. You could sort of gradually approach the isostatic solution under this technique, right? If you didn't do this, it would be kind of very stochastic how you'd get to the isostatic solution, because there's always a family of answers. But this one would sort of maybe smoothly approach you to the isostatic solution.
Curious if what you
Yeah.
know about the overlap that you.
Yeah. No, I mean, what's interesting is indeed, if as you approach isostatic, the thing you will converge to that answer. Yeah. Yep.
So this reminds me of another technique where you take a big MD step and then you use tangent gradient to solve for the fast overlaps. And one of the problems there is that there's more than one minimum you can go to. How do you know your energy function doesn't have multiple minima, even on this trough? How do you know there's not multiple minima there? Fall into. Now, in these cases, you're very highly constrained because you have way more context. So
Yes.
it'd be unlikely that you find them. But as you look more toward isostatic, at least in these other types of methods, you do find there are multiple paths. You can even think about from your original 3-point problem.
Sure.
There's an unknown initial displacements. And depending on which ones I pick, I'll get different minima
Right.
when I push on that guy. Depending on exactly.
So what happens though, it's a good question, but what happens if you reframe it in terms of forces, not displacements? Is there only one minimum in forces?
You don't do it that way. And
Exactly, that's the thing. In regular DEM, the master is the
but the
displacement.
problem is that you do get discontinuities in the force. And that's.
Yeah, so the discontinuities I'm not so concerned about, because you do a classic step first, which already solves complementarity, right? So you're only searching through, so the forces can just turn to zero. That's okay too.
Sure.
Yeah, so all I can tell you is that second step, the E of F function, right? It's just a quadratic function. For example, if it's Hookean, it's just a quadratic function of F.
But it's a quadratic function of a bunch of things, right? It's like.
It's a quadratic function of just,
energy landscape.
but it's only force, right? So everything you're thinking about is in the subject to part,
Yeah.
right? But that's a convex set. That's actually convex. We actually proved that's convex, right? So it is a quadratic function of a list of forces subject to a convex space that you can search through for the forces. So there should only be one solution.
You'd say there's only one.
I would say there should be one. Yeah.
Interesting.
Yeah. Yeah. Any other,
Yeah, I'm just curious. I mean, you're summing up complementary energy, but actually it's the strain energy which is summable. And right, is the right energy when you sum up the. you get
Okay, so
x
why am I
squared.
going complementary and not strain energy?
Well, you want to work with forces.
So I want to work with forces, so
Yeah.
it's the Legendre transform of the
No, that-
typical energy.
That's clear, but
Right.
I'm not sure that. I mean, the energy, if you sum up the strain energy, it's a summable property, but when you can't really sum, maybe in this case you can, but.
Well, yeah, so-
But once you get friction and you do.
Yeah. There are subtleties when the friction comes in that I did not have time to go through.
Right, yeah.
Okay, but one of the, I mean, if you asked about friction, one of the things we had to do. Let's see how fast you can read, right? I went through this slide very quickly, okay. It's to do this correctly when there's friction, it's really hard to do it if you say that the subject to condition uses the updated values of the force. So the typically, right? So for the friction condition, I'm using the old normal force here to bound the tangential part. But the new normal force must always be greater than or equal to 0. This is something you do because otherwise so whenever you have inequality bounded optimization, the Lagrange multiplier method becomes the KKT method, right? And when you do that, it still looks like Lagrange multipliers, but you have slack coefficients, okay? And the slack coefficients don't quite work out if you make this the updated normal part. You get what we call normal pollution, okay? Where the condition for the normal force, you see some tangential stuff showing up in there, okay? But if you make this thing right here, which is what I just showed you the result, it still works quite well and it actually works out perfectly. This will exactly turn right back into DEM with tangential and frictional slip. But you're going to be slightly offset because this uses the old normal force rather than the new one. So at the end of the step, it might not be perfect Coulomb. It'll be this. Yeah. So friction's a little weird. I agree with you on that. Yeah. But to the question of can I add complementary energy? I guess one thing I could say is, well, any way you slice it, when I showed you the Lagrange multiplier, you see that it does work.
Yeah, I guess it is a cost function.
It's just a cost function. And when I take its gradient, it suddenly turns into the overlap.
And then it's elastic.
Yeah, now it's just elastic.
In that.
Exactly. Sound good? Should I quickly go through part 2?
Yeah.
I can do part 2 much faster. Part 1 was more mathematically interesting than that. Okay. So you tell you, I've never talked about this stuff before, have I? No.
Never saw that.
Okay. So, new methods for obtaining forces. Anisotropic Hertz relations. Okay, let's talk real quick about how so let's go back to the world of soft DEM. Okay, so I told you how to get rid of tracking overlaps. And now let's go ahead back and track overlaps. Okay. So let's remember how we would do DEM for sort of arbitrary shaped particles, right? That were smooth. Okay, so there's some sort of a force law. Each particle has a location and an orientation marked by some angles, right? And I put them in contact and there will be some overlap delta, right? And there's some contact force between them. So how would I get that force? Okay, so one way to do it is, hey, you can mesh the whole thing or analytically solve the elasticity problem within each grain. Okay, that's one way to do it. Or you could get some sort of an empirical force law. Now, if you consider how you do this, if the particles are made of an isotropic material. So isotropic here is just what the particles are made out of, not their shape. Okay, so they're made out of, I don't know, polycrystalline metal or something, right? Our good friend Heinrich Hertz, who I sadly didn't live very long. I learned while making this. Poor guy didn't really make it to 40. I don't know what happened. All right. Well, anyway, it was the 1800s, so maybe that was the typical age. I don't know. So Heinrich Hertz came up with this relationship here by analytic. He actually solved it. He solved the math problem that basically figured out how to approximate the PDE solution from elasticity. And it says that the force between the particles has to do with this thing called the effective plane strain modulus and some function of the geometry. Now, if both particles are spheres, it's just r to the 1/2. But there's some known function of the geometry of the two objects times overlap to the 3/2, right? That's our friend from the Hertz relation. We all remember it's overlap to the 3/2. Okay, and this plane strain modulus has to do with the elastic properties of object I and the elastic properties of object J. for the two bodies, right? So now let me ask you a question. Let's suppose in the world of small, right, which is where we got into this project, you might start with a piece of polycrystalline metal that looks isotropic. So typical metals are polycrystalline where the crystals are oriented in every direction. So you can just sort of blur it out and say it's isotropic. But let's say I get small enough that each little particle looks like it's one crystal. Okay. So now the elasticity formulation that I would use for that particle is no longer isotropic. It will have crystalline directions, right? And so we actually did a project where we had to do this because they were creating some powder where they literally like manufactured each grain could be made out of like one or maybe a couple crystals. Okay. So can I generalize Hertz's relationship when the elasticity of each grain is anisotropic? And how could I exploit the answer? Now, what I'm going to do is give you a little bit of a teaser on what the answer comes out to look like, and then I'll show you how we got there and what you can do with it. So if each particle has some orientation, okay, particle I and particle J, and when they're contacting, there's a normal vector where they touch. That normal vector can be drawn in their orientation space. Each one's, because of how they're oriented, will sort of look at that normal vector from different views, okay? And I can describe two angles to explain where that contact vector looks according to particle I and to particle J, two sets of angles apiece. And so when you actually work through the whole solution, I'll show you how we get to this. It looks a lot like Hertz's solution, except for the following. That thing that was the plane strain modulus that depended on just the Young's modulus and Poisson ratio of each grain. Now it depends on those things, but also on the sets of angles. And the function of geometry is actually fairly similar to the one that Hertz found. If they're both spheres, it'll just be r to the 1/2 again, but otherwise we have a formula for this. So what is this? How do we do this? Okay, so let me quickly talk you through the way that you would solve this problem. Okay, so you got two arbitrarily shaped particles that you're pressing together. Now let's suppose right as they barely touch, there's this thing called the gap function, like I told you before, but it's a full function now, right? I look at this sort of plane where they touch, and the separation between the surfaces is a function of where I am on that plane. Okay, that's called the gap function. 5 minutes, I can do it. I can do it. Okay. And so if I'm close enough to the surface, the gap function will look like a quadratic function because everything looks, I took calculus, I know how this works, right? It goes to 0 and it's, the linear term is 0 at 0, so that's the first order term. So if I look close enough at the gap function, it will look like some sort of elliptic paraboloid, okay? Now, as I press them together, I'm going to establish some kind of a contact force, right? And I'll get that force through a pressure distribution over a contact area. So this was how they started, right? They were barely touching, and now I press them together, and now there's like a flat thing between them, right? And where they're touching, there's pressure. And if I integrate through that pressure, I'm going to end up with the contact force. And so if these were the contours, these dotted lines were the contours of this, which was what they looked like when they were barely touching, that's just a gap function. When they touch, especially if they're anisotropic or have funny shapes, you might get like some first order ellipse-shaped contact patch that might not match up with this. But if I integrate through this, the pressure, I should get the contact force, right? Whatever it may be. So let's just talk about kinematics for a moment. So if, just to make things easy, let's suppose you had just a flat rigid surface and you're just compressing down on this lumpy anisotropic elastic thing, okay? So here's the rigid surface, and then I move it straight down to get some contact displacement, so-called delta, right? At each point where they touch, right? The gap, this was the original gap, and this is how much it must have moved just elastically, and all of this must be flat, right? So you get this kinematic relationship, which says that W must equal delta minus the original gap, right? So that's like a kinematic constraint of the contact that says whatever the gap was, you add the elastic displacement, and that needs to be where the contact plane now is. Okay, so let's take that and talk about how we would actually solve the elasticity problem. Yeah, this is the part that I told you I could do quickly. So you actually have to do this like super brute force, all right? I'm sorry, okay? I really apologize. You have to add the Green's function, and it's an anisotropic Green's function, right? So there's some Green's function, like let's look at particle kind of V1, right? Where you have to imagine that on the surface that you're looking through, there's some unknown pressure distribution, okay, E. Each pressure distribution causes a displacement according to a Green's function. And the Green's function depends on how far you are from the point of contact, as well as the orientation and the normal direction and the reference x direction n. Very complex, but you can actually solve this. So this is actually solvable, but it's very expensive to do so. Okay? But there is a little trick you can do where this dependence on n can be removed through an azimuthal average, and that actually makes the problem tractable. And that's how we get the thing that I showed you right here. Okay? And so once you do that, you get a nice relationship, like I showed you in that first slide, that relates just the angles for body B and the angles for body B2 through one relationship here. And what's nice is that this relationship that depends on all these angles, it just depends on some function of the pair apiece. And this function, what we do to make this like tractable as like a DEM algorithm is we just store it as a lookup table. Okay, so we actually just pre-compute. There's this function E star of alpha and beta. And it's just a table. Here's alpha, here's beta. Okay, and we can, there's elliptic integrals in here, but that's okay because we pre-compute it. So you just do it once. And then whenever you've got two particles that touch each other, I say this particle is this orientation, this particle is that orientation, and they touch. Okay, fine. What's the alpha and beta for this particle at the contact? What's the alpha beta of this particle? Look up this number, look up this number, shove it up this side. Okay. And so maybe I'll just, these are the validations that we can actually match with this method, finite element solutions. The approximation and the exact solution agree with each other for lots of different possible crystal structures. Because you know in elasticity, when it's anisotropic, there's like, you might need like 81 coefficients or something. Well, anyway, if you have a cubic lattice like iron, you need 3 coefficients of elasticity. Quartz needs 6. Zirconia is my favorite. It's monoclinic, you need 13 coefficients. But the good news is that this method seems to work pretty well. So real quick, what can I do with this? So let's go back to my friend, the cannonball packing, right? And so let's look at zirconia, which is really anisotropic. And so the way I'm going to draw this is, I'm going to put a little white line around the equator of each particle. Zirconia is, because of the way that it's anisotropic, it's like stiff at the north and south pole, and it's sort of soft around the equator. Okay, that's just like a little mnemonic for you, okay? So look, the white lines and the stuff that I show next is the equator, okay? So I'm going to stack a bunch of zirconia particles and use my contact method. And you can see how the forces distribute depending on just the orientation of the particles, okay? All of the same particles, they just rotate some of them, right? So it's pretty weird, okay? So now this one you don't see the white band because you're looking down. Basically, all of them are just oriented north pole. Here, you orient them all this way. Here, you just have a stripe where everything on that plane coming up out of you is oriented like you're looking at the equator. And this one, you oscillate them. And you can see just by rotating the particles, you can really screw with the force distribution because the particles are anisotropic. So different things are touching and the stiffness is therefore changing all over the place. So it's kind of interesting. Another thing you can do with this is, let's suppose that you're NASA and you need to create some kind of acoustic thing with band gaps, right? Usually on the fly. To try to create something that has band gaps, usually you have to make it accordingly, right? But with this, you can make a string of beads. And if you have the freedom to rotate a couple beads, you can tune the band gap however you want, okay? So for example, if you just have a string of these anisotropic particles and you control the angle of tilt for, let's say it goes like vertical, vertical, tilted, tilted, vertical, vertical, tilted, tilted. If you control that angle of tilt, you can actually tune the band gap sequence. So you can decide what frequencies to filter out without having to change the particles. Okay, so it's a cool little application of this. You can make a shock absorber to absorb frequencies on the fly. Okay, so what did I just show you for part 2? So we started out with a green function representation that was exact but crazy. Okay, we simplified it. I showed you very quickly that the simplified solution seems to match the exact well enough. And now we've got something that's actually in a DEM code. It basically uses a lookup table, and it runs just as fast as regular DEM. Okay, I'm done.
Sorry for the spread, huh? I learned something new. I think I saw like 5 different things that Ken has done, and every time I'm overwhelmed. Nice to see a new thing. That's great. Thanks so much. Of course, we had already a few questions, and the time is running out. Although we started 10 minutes late, so I'll say let's do 5 minutes max, so that we could get Rose later preparing. Yes, Gary.
And if you want to do elastically isotropic arbitrarily shaped particles, can you do those without the lookup table pieces and that, or is that still?
Elastically isotropic, yeah, you could do that without the lookup table. All you would need to know is locally where they touch, what are the curvatures at each side, and then on the fly that lets you make the gap function. And then you can use Hertz's relationship, because once you've got the shape of that gap function, it'll convert that to an effective radius. And that's the thing that goes into Hertz's relationship. So Hertz's relationship, the only hard part is this. But if you know what the gap function looks like, because you just follow that, you create it on the fly, then you can run Hertz. Yeah, so if it's isotropic but weird shapes, where they touch, you can create an effective curvature, and then you just throw that into Hertz, and that'll work.
Question? Yes.
Yeah, the orientation of the last example of those particles, are they fixed by hand, or do they form some sort of orientation, or they made spontaneously?
Oh yeah, so for this example, you talk about this one here?
Exactly.
Yeah. So this one was just sort of fun for us. We fixed it by hand. We arbitrarily picked like up, tilt, up, tilt. Actually, if you go up, tilt, it doesn't work as well.
Okay.
Doesn't. Yeah, you can show when you actually calculate the acoustic nature. So you'll see that you don't get much band gap change. But this one, you get big band gap. This would be an open question for you guys. We talk about open questions, right? Can you actually reverse engineer this? So we just showed that you have freedom to start changing around the band gaps by changing how you tilt the particles. Because as you tilt the particles, the parts that touch have different stiffness, right? And that's exactly what you would need to play the band gap. Can you reverse it? So let's suppose I say, look, I need to filter out this one, and this frequency, these frequencies. Here are the particles I have. Here's their structure. How should I position them? How should I orient? That would be a cool question.
But do you think there would be a unique solution?
I have no idea. I mean, if you have a whole set of frequencies you want to filter out, the more, of course, constraints you give it, the fewer solutions there should be. But if your unit cell could be arbitrarily large, you could probably filter out anything, right? Yeah, you could have multiple angles of tilt. In the end, it's actually not that bad, because once you pre-stress a string of beads, right, then it goes back to being a linear acoustic problem again, right? Because that 3/2 power only really matters when delta is very close to 0. So if you pre-compress it, it's locally linear. So you can actually use linear techniques to get these band gap diagrams.
Yeah, sure.
If and I were just noting and talking when we were talking. Sorry about that.
So that's what I always do.
We were thinking, so that people are doing like hacking of Ruby particles.
Yes, like Ryan, right?
Yeah, that's what.
Yeah, Ryan. Yeah.
So do you think you can validate some of them?
Last time I saw Ryan, I was like, "Could you do this?" And he said yes, but I don't think he's done it yet.
So the thing is that the diffraction is affected by the orientation.
Yes.
If you do extra diffraction.
You could check.
Right?
He could do it. He could look at it and go, "Yeah, you oriented them according to what you said you would do." I'll tap it. You can do an ultrasound thing and maybe see if it's passing frequencies. Yeah.
Definitely there's something here to benefit in how they do it.
Yeah. For sure.
I don't think they take the anisotropy explicitly
Yeah.
into effect. That's
So when Ryan does his thing, he just assumes isotropic, but it's Ruby and it's
Yeah.
perfect crystal. So
Yeah.
now it really is. Yeah.
I think we can continue discussion with Ken very soon, because we're starting with a group for
Yeah, so come outside now, just the electric doors for a group photograph, and then you can at last have coffee.
And so finally, I want to thank again Ken for an excellent